There are several important results to be noticed from this equation. First, notice that even though we're talking about the same two events, light leaves point A, light joins point B, the time between them is not the same. The time recorded on clocks in the laboratory or on clocks in the spaceship are different. So we no longer have that sense that time is the same in all frames of reference. Second, this links both space and time to a single quantity that's much like a time. In other words, we've linked space and time together. This is something that's invariant in all reference frames, but it combines both space and time. We can't think of them separately. Three more key things. Anytime we have two events, event A and B, the time between them is not the same in two different frames that are moving relative to each other, the rocket frame and the laboratory frame, for example. However, even though the times are not the same, any observer, if they can measure the time on their clock and how far apart two events occur, can figure out the time on the rocket ship clock, the time on a clock where the two events happen at the same place, simply by using this formula. And third, as I stated before, this part is in a frame of reference where the two events A and B happen at the same place. That makes it special. And this quantity, c delta t squared minus delta x squared, is the same regardless of what other frame we measure it in. It's an invariant. So if I were to measure in a frame moving slowly compared to the rocket, or if the rocket were moving slower compared to the laboratory, c delta t would get smaller and delta x would also get smaller, but their difference would stay constant.